Okay, so check this out. You found a 9-volt battery because that fire alarm detector, carbon monoxide detector in your house has been beeping for the last week, and you don't have any of these other than this one in the house, and it's going to take a couple days to order a new set. So we want to, before we put this in and go through all that beeping and blaring when you take one out, we want to know, does this 9-volt battery work? So check it out. I have a little cup of water here, and I have some old holiday lights that I ripped apart because the bulbs weren't working. That doesn't mean this wire doesn't work. So to help this little demo work, I'm going to put a little bit of salt in my water. This will help allow charge to flow through here, possibly. So I'm going to connect one of my wires up to one side of this battery. Okay, it's kind of a pain, but I got that. Okay, now I'm going to connect the other wire up to the other side of the battery. And tried this a few times. Let's see if you can see this now. So I'm going to put these two wires in my water, and one of the electrodes, or one of the wires, has bubbles forming all around it. So this is telling me that this 9-volt battery works. So what I'm actually doing here is I'm separating water into oxygen and hydrogen gas, and we can see those gases forming on the ends of that wire. So kind of weird that we're separating water into hydrogen and oxygen gas using this little 9-volt battery. So what does this help demonstrate? This helps demonstrate that we can not only make a battery using redox reactions, but we can force some reactions to occur using a battery. So that's this concept of electrolysis. So electrolysis would be all about using a battery or using voltage to cause a redox reaction to go in reverse. So what we just saw there in that little cup there would be the opposite of this reaction. So hydrogen gas likes to react with oxygen gas to form water molecules. And I can go ahead and balance this really quick. So if we look at our oxidation stage, element 0, hydrogen always +1, oxygen's a -2. The hydrogen is going up, so it's being oxidized. The oxygen is going down, so it's being reduced. So in this reaction, this is a spontaneous reaction. You know, once you give it a spark, hydrogen gas will naturally combust to form oxygen, and it is a redox reaction. Now, water does not spontaneously turn into hydrogen gas and oxygen gas. You know, this will not just happen in nature. But if we hook this up to a battery, we can then force this reaction to go in reverse. So this process is called electrolysis. This is also an interesting application in that if we set up our little battery from last class, and I have two electrodes in here, and I connect them with a wire, and I connect them with a salt bridge. If I have my battery from last class, and let's just say the electrons were going in this direction naturally. So this is producing a voltage. We could put a little light bulb up here and the light bulb would light up. But what if we wanted to do something different? What if we wanted to put this metal, you know, let's say it's like copper, in a solution of silver ions? And what if we want to coat this copper with silver metal? Well, all we have to do is take away that light bulb and put in a battery. And the battery can now force the electrons to actually flow in reverse, and it can maybe cause this silver to coat this copper. So in your computers in home, in most of our electronics, we actually have some gold now. You know, some people try and extract that gold using all these complex, usually unsafe experiments. But that is not pure gold. Pure gold's too expensive to use in these electronics, at least for now. So what they do is they coat some cheap metal with a tiny bit of gold. And the gold is so useful because it's both conductive and non-corrosive. So, you know, it will not corrode with gases in the air or with other chemicals very easily. So this is called electroplating, and this is again just using a battery to cause a redox reaction to go in reverse. Now I want to just show you some sample problems related to electrolysis, and then we will actually be done for the year. Let's check out these two reactions. For the following reaction, identify whether it would be spontaneous or not. So I'm going to do a little redox table here. Redox. And look at this reaction. The silver is going from +1 to a 0. That means the Ag plus is being reduced. So that means the Ag would be here and the Cu would be here. And if we look on our standard reduction potential chart, we see that Ag has a standard reduction potential of 0.80 volts. And copper, which is going up here, it's being oxidized, it's going from 0 to +2. Copper, and it's a +2, so that would be 0.34 volts. 0.8 minus 0.34 is a positive value. So yes, this one is spontaneous. Now what about this bottom reaction? Will silver metal react with copper ions to form silver ions and copper metal? Well, silver in this case is a 0, +1, +2, and 0. So if we did another redox table this time, we would have the silver being oxidized and the copper being reduced. And then you would set it up like 0.34 volts minus 0.80 volts. And that means we get a negative value. When you get a negative value, that means that reaction is not spontaneous. It means it wouldn't happen unless you hooked it up to a battery. And then you would have to use a voltage to cause that to work. Okay, now I want to show you some kind of weird plating questions here. And these plating questions just require us to do some, I don't know, I think kind of interesting unit conversions. So there's two other little new units you need to know about. So the first is an amp. An amp is abbreviated just with a capital A. If you want to think about a huge tub of water, you know, I'm kind of thinking about like my rain barrel outside. The volts is the amount of water inside the barrel. It's like that amount of energy that can flow. An amp is how fast it flows. Amp is all about speed. So amp is about how fast my water can flow out of that rain barrel. So amperage is like a speed, and voltage is like the amount of that energy. So the unit of an amp is actually called a coulomb per second. And now what the heck is a coulomb, a capital C? Well, a coulomb is a unit of charge. And in this unit, charge is really all about electrons. So a coulomb is equal to 96,480, oops, I don't want to do the one over. 96,485 coulombs is equal to 1 mole of electron. So again, an amp is like the speed of this electron travel, and then it's measured in coulombs per second. And then a coulomb has to do with electrical charge, and 96,485 coulombs are equal to 1 mole of electrons. So let me just show you two problems here, and then we're going to be done for the year. And then you can try the practice too if you really feel compelled to. So here's some questions, you know, people might actually want to know. How long would it take to plate out 0.5 grams of copper in a CuNO3 solution with a current of 2 amps? Whoa, this is kind of goofy here. So what we're going to need to do here is first start out with that CuNO3, and I want you to think about the charge of the copper in there. So CuNO3, NO3 is always a -1. You know, we get that from that polyatomic ion chart from earlier in the year. And we have 2 of them there. So that means this copper must be a +2. So once we see this, I want us to figure out the charge of the copper. This is going to come into play when we talk about our electrons in a minute. Now, for this type of problem, let's start out with our 0.5 grams. So we have 0.5 grams of copper. And this question is talking about how long. Now, the only unit we've talked about in regards to time is seconds, when I talked about that coulombs per second. So I'm going to get my seconds unit over here on the right. So I'm trying to get from 0.5 grams of copper, and I want to know how long it would take to plate this copper, 0.5 grams of it. So now, grams is no good. I'm going to say like 63.5 grams of copper is equal to 1 mole of copper. Grams is no good. So now we have moles of copper. Now I'm going to say 1 mole of copper is equal to 2 moles of electrons. Do you see how this is a copper plus 2? For every 1 mole of copper you have here, you would need 2 electrons to be transferred, because this is a plus 2. Okay, now, 2 moles of electrons. I need to cancel out moles of electrons. Now I know that 1 mole of electrons is 96,485 coulombs, because I just gave you that information a little bit earlier. And then we know that a coulomb per second equals an amp, and this problem said we have 2 amps, which means we have 2 coulombs per 1 second. Remember, if it's 2 amps equals 2 coulombs per second, and I need to take the inverse so my units will cancel. So now we can actually, like scientists can calculate how long would it take to plate this copper, to plate this other metal, or to plate this copper on there. Okay, let's try one that's kind of going backwards. I'm going to try this question. What type of current? So type of current means how many amps would we need to supply? This other one in here is kind of the same. Would it take to plate out 0.75 grams of copper from a CuNO3 solution in 60 minutes? So we're trying to solve coulombs per second in this one. Okay, now again, I think we should start out with our solution here to figure out the charge. So NO3 is a -1, copper is a +1. So if I have 0.75 grams of copper, and I know 63.5 grams of copper is equal to 1 mole of copper, and I know that 1 mole of copper this time has a charge of +1. So for every 1 mole of copper plated, you would need 1 mole of electrons. And then I know 1 mole of electrons is equal to 96,485 coulombs. So first we would solve for the coulombs. And then if you want to get amps, coulombs per second, you need to divide by seconds. Well, 60 minutes, 60 times 60 seconds is 3,600 seconds. So you would take this coulombs, divide it by 3,600 seconds, and again, a scientist could figure out exactly what type of current or what type of amps you would need to apply to 0.75 grams of copper using a CuNO3 solution if you wanted to plate that metal in 60 minutes. So why is this useful, this concept of electrolysis? Because we can force some reactions to go in reverse using a battery, and then we can also plate metals, so we can cause these redox reactions, these battery reactions, to go in reverse using a battery. Okay, that was our last concept of the year. I hope it was a little final practice with unit conversions, and I hope that explains like how batteries can be useful.